Hello everyone, welcome to this session. I'm Chen. In this talk, we are going to introduce our lab's work on multi-view stereo. We have three presenters here, Dongfang, Shuocheng, and me. This is the outline of this talk. First, we'll give a brief introduction to MVS and the current classical and learning-based MVS. Then, we'll present three works in details. Finally, we'll conclude the talk and give some potential future directions of our lab. First is the introduction to MVS. The target of multi-view stereo is to reconstruct the dense 3D shape from a set of images and camera parameters. MVS has been applied in various fields. First is AR and VR, like the recent iPad Pro. If you want to place the virtual objects at their proper locations, you need to first measure the 3D scenes accurately first. And robot manipulation, which needs real-time visual feedback to adjust its control strategy. Also, the remote sensing to reconstruct the architecture from a large number of photos captured by drones. There are four requirements of MVS: the depth range, accuracy, time efficiency, and computation efficiency. For the depth range of remote sensing is the largest, like hundreds of meters, and robot manipulation and inverse engineering often are operated in 1 or 2 meters. For accuracy, the inverse engineering requires the highest level of accuracy for MVS, usually sub-millimeters. For time efficiency, AR and VR requires real-time reconstruction of the target scene, like 60 FPS, while the remote sensing and inverse engineering could be done offline, so it doesn't matter if it takes hours to reconstruct the shape. For computation efficiency, AR and VR are usually performed on mobile devices like phones and tablets, while the remote sensing and inverse engineering could be performed on PCs with powerful CPU and GPU. Now we introduce current classical and learning-based MVS. Reconstruction from silhouettes is one of the classical MVS methods. In this method, you need to first identify the silhouettes of the object in each image, and then back-project each silhouette into the 3D scenes. Intersect the back-project volumes to get the final 3D shape. The advantage of this method is that it is easy to implement and fast. Also, it can be even accelerated using arc trees. However, the drawback is that you need to first identify the silhouettes. The result may not be photo-consistent, even though it agrees with the silhouettes. And also it can only reconstruct single object, not 3D scenes, and it cannot reconstruct concave shapes. Another classical MVS method is reconstruction from photo-consistency. It searches the corresponding pixel along the epipolar line using photo-consistency. Two metrics that are usually used are NCC and SSD. The advantage of this method is that it is much more accurate than the reconstruction from silhouettes, and it is able to reconstruct the concave shapes. However, it requires the texture for photo-consistency computation, and also it is sensitive to non-Lambert areas, which look different in different viewpoints. So, for classical MVS methods, there are several main limitations. First, they cannot handle textureless areas, where it is hard to identify the silhouettes or measure the photo-consistency. And it is difficult to handle reflection, transparent, and repetitive patterns in the image as well. Recently, deep learning has shown great success compared with classical counterparts in various fields, such as object classification and object detection. Therefore, people started to use deep learning for MVS to overcome the limitations I mentioned before. The first work that used deep learning for MVS is Zomta's work in CVPR 2015. They used CNN to predict the matching cost of two local image patches in two views. It's like just replace the traditional photoconsistent metric with the learned metric, and the post-process remains the same. Therefore, this method is not an end-to-end method. The first end-to-end learning-based MVS method is proposed by Kendall in SCCV 2017. In this method, they build two cost volumes and use 3D CNNs to predict the disparity between two rectified images. Therefore, the network can be trained end-to-end with the supervision on the disparity prediction. For the unstructured multi-view stereo, where the images are captured at arbitrary viewpoints, Yao proposed to build a cost volume in the reference camera frustum and walks image feature of source views into it, using differentiable homography. Also some similar works after MVS. The advantage of the learning-based MVS method is that, first, it uses the learned feature instead of the handcraft feature. Therefore, they can get more robust matching. And they can combine the shape prior in the learning process. Therefore, they can get more complete reconstruction. One key component of this learning-based MVS method is the 3D cost volume. However, there are some limitations in the current cost volume-based MVS method. First is the memory consumption of the cost volume is cubic to its resolution. Therefore, this kind of method is not feasible for high resolution and accurate reconstruction. Another limitation is that in existing methods, they do not consider the consistency between the depth prediction and local geometry features. Therefore, the depth prediction can be very unsmooth and far from the ground truth for textureless areas.
Good afternoon, everyone. Thank you for this introduction. I'm Songfang. Here I will present our work point-based multi-view stereo network. As introduced in previous slides, learning-based methods have attracted a lot of interest as they propose more robust features than the handcraft features used in traditional methods. Also, learning-based methods generate more complete results than traditional methods. However, we observe that existing learning-based methods generally need to build a 3D cost volume and apply 3D convolutional neural network. The 3D cost volume is memory cubic to resolution. Thus, these methods are not feasible for high-resolution reconstruction. Here, we revisit the construction of 3D cost volume and propose a more efficient method for depth estimation. Given the multiple images and the camera parameters, 3D cost volume is built in the frustum of the reference view. For each voxel in the volume, it gathers features from the multiple images by projection. The main intuition lies that the image appearance at the correct depth should be consistent across views. Based on this, previous methods used dense 3D convolutional neural network to predict the size of the cell. So one question is that, are all these 3D convolution operations necessary? Actually, the depth map is just a curved surface in the 3D space, and most of the 3D convolution operations are applied in areas far from the surface which are not necessary and do not help the final depth prediction. Based on this observation, we use point cloud to represent the curved surface and process the surface points directly. Compared with voxel representation, point cloud is more suitable and efficient to represent the sparse curved surface in the 3D space. Generally, our network is composed of two parts. First, in order to carve out the approximate target surface from the whole 3D space, we first use existing method to estimate a coarse depth map from viewed images. Afterwards, we focus on the neighborhood of the target surface and use our point flow model to refine the depth map, which saves us from unnecessary computation. Additionally, this refinement can be performed iteratively. Taking the memory usage into consideration, the initial depth map is in low resolution, and we unproject the coarse depth map into 3D space to get the initial point cloud. Then comes our main contribution, the point flow model. The goal of the point flow model is to refine the input depth map by moving the unprojected points along camera directions. We call it point flow as we are trying to predict the offset to the ground truth surface. Then, we power the points with image features fetched from the multiple images. Also, every point maintains its XYZ location. For the image features, we use the multi-scale features for more robust feature matching. But regression the offset for unprojected points is still challenging from our experiments. To facilitate learning, we propose the point hypothesis. The point hypothesis is a sequence of points with different offset along the reference camera direction. Besides, we fetch the point features for the hypothesized point. With the help of the hypothesized point, we convert the offset regression task to classification task. The final point flow is predicted as the expected offset among the hypothesized points. Spatially, we use the edge convolution to predict the probability of each point hypothesized. Here, I have shown how we refine the depth map with the proposed point flow model. Additionally, benefit from the flexibility of the point representation, our point flow model can easily be used iteratively. For every iteration, we update the point features, which enables us to get the more accurate features around the ground truth surface area. Also, we support custom depth map interpolation before sending to the point flow model. Next, I will discuss the results of the point-based multi-view stereo network, including the reconstruction quality, memory usage, and other evaluation experiments. Our network is trained on the DTU Benchmark, which contains 49 views per scene under different lighting conditions. As shown in the F-score table, our method outperforms both traditional methods and learning-based methods. Compared to the MVS-NET, which is the state-of-the-art learning-based method, our depth map resolution is almost 5 times higher, while our memory consumption is smaller. This figure shows qualitative comparison with MVS-NET. The second row is the colored point normals zoomed in the window rear. As shown in this figure, our method can reconstruct more geometry details than the state-of-the-art. Also, compared with the traditional method, our method can generate more complete results than the traditional methods. To demonstrate the effectiveness of the iterative refinement, the reconstruction results at different iterations are shown here. With more iterations, we get more sharper and more geometry details. Moreover, benefit from the points representation, we can choose to only refine the depth in the regions of interest instead of the whole depth map. For example here, we give higher resolution at the balcony rear. Also, we show the reconstruction results on the tanks and temples benchmark. The reconstruction result is evaluated without further training. Here is the video of the reconstruction samples. We compared our method with the MVS-NET and the errors are colored. It appears we can get more accurate reconstruction results than MVS-NET. And this is on the tanks and temples benchmark. The target surface of the multiview stereo is sparse in the 3D space. To conclude, our point MVS-NET use point cloud representation that concentrates on the neighborhood of the target surface, saves unnecessary computation, and achieves better time and memory efficiency. Besides, benefit from iterative refinement, our reconstruction gets higher and more accurate geometry details. Thanks for listening.
Hi everyone, my name is Shuo Chen. I'm working with Professor Hao Su on learning-based 3D reconstruction. Today I will introduce our paper Deep Stereo using adaptive thin volume representation with uncertainty awareness. This paper is accepted to CVPR 2020 with oral presentation. So from previous discussion, we already have a basic understanding of the cost-volume-based 3D reconstruction, and the crucial step is to discretize the 3D scene. And we know there are two factors that can affect the reconstruction quality: the completeness, which is related to the depth map resolution, and the accuracy, which is related to the number of depth hypotheses along the camera ray direction. To achieve high accuracy, you need to sample a large number of depth hypotheses along the camera ray direction. And to achieve high completeness, you need to predict a depth map with very high resolution. And with limited memory, there is an undesired trade-off between the accuracy and the completeness. And we know the fact that the object surface only occupied a small number of voxels, and the cost volume is empty in most areas. So we ask the question, can we find a smart representation of the 3D scene that's both computational efficiently and friendly to the learning framework? We found some positive answers in the past 6 months. Our high-level idea is different from previous methods that partition the space uniformly. We proposed a cost-to-fun solution that adaptively sampled the 3D space. So, more specifically, given the prediction from previous stage, we can estimate the confidence interval, and for the next stage, we only sample the depth hypothesis inside the confidence range. This allows us to reduce the sampling space and to improve the computational efficiency. So here I will introduce the details of our proposed method. So we first extract multi-scale features for each input view using a 2D U-net. And at the first stage, we uniformly sample the depth hypothesis to build the cost volume, and then we apply a 3D convolution to regulate the cost volume and get the probability volume. With the probability volume, we can calculate the depth map by compute the expectation of the cost volume of the probability volume along the depth direction. So, with the probability volume for each location in the 2D image space, we can take out a probability distribution. And now the question is how to compute the confidence interval for a given probability distribution. We can calculate the variance of this distribution and the corresponding standard deviation. And then the confidence range, also known as the uncertainty, is determined by the expectation minus lambda times the standard deviation and plus the lambda times the standard deviation. And we only sample the new depth hypothesis inside this range. And please note that for every location, it has its own probability distribution and its own confidence range. This allows us to generate the spatial varying samples that capture the local geometry details and reduce the computational cost. So we resample the depth hypothesis using the estimate uncertainty. And since the uncertainty range is more concentrated, we can reduce the number of depth hypotheses and increase the spatial resolution. Our full model will predict a high-resolution depth map that captures fine-grained geometry details. And here we show the narrowing process of the 3 stages. So we plot the RGB images, the ground truth depth, and our depth prediction. And the next 3 subfigures shows the probability distribution and the estimated confidence range. The y-axis shows the probability, while the x-axis shows the depth values, and the purple region is the estimate uncertainty. We can see that from the stage 1 to stage 3, the confidence range is gradually concentrated to the ground truth depth, and the estimate depth will finally converge to the ground truth. And here we show the point cloud generated by the depth map from our 3-stage. We can see that our full model will gradually densify the local geometry details and reconstruct an object with rich details. Here we show the speed and memory of our model. Our full model is much more faster than previous method, and we consume less memory than the state-of-the-art method. Our full model can predict the depth with full resolution, which is larger than previous method. And here we show the quantitative results on the DTU dataset. Our model outperformed previous method by a large margin. And here we show our results on the text tempo dataset. We directly test our model without any fine-tuning. The results shows that our model can generalize better. Here we show the qualitative results on the DTU dataset. We can see that our full model will predict the 3D point cloud with more geometry details. And here we show the qualitative results on the text tempo dataset. To give a conclusion, that we proposed a cost-to-find method that adaptively samples the 3D space. Our model is time and memory efficient, and we can produce better reconstruction quality.
Hello everyone, now I present our work, Noble Assisted Stereo Depth Prediction, which has been accepted in CPR 2020. As mentioned before, there are some fundamental difficulties in MVS. That it's difficult to find correspondences for areas with weak texture or repetitive patterns. Therefore, the predict depths can be very unsmooth and far from the ground truth, which is not applicable for certain applications, such as AR or VR. However, experiments have found that it is much easier to predict accurate normal for these areas. The intuition here is that, like human beings, when humans see a wall, it may be difficult for him to predict the distance of the wall. However, it is much easier to predict the normal direction of the wall. Therefore, in this work, they use depth normal consistency to jointly learn depth and normal prediction. First, we use the multi-view image information to predict the surface normal. We build a 3D cost volume using image features and work coordinate. Apply CNS on it, after which, to decrease the computation amount, we divide the cost volume into slices and use 2D CNNs to predict the normal of each slice. Then add them together and normalize it, get the final depth prediction. As shown here, our multi-view normal prediction is much more accurate than single-view depth prediction. After the normal prediction, we aim to force the consistency between depth and normal. Therefore, we use the camera pinhole model here to compute the depth-normal relationship. Then, we use the Hilbert laws to constrain the consistency between the depth prediction and the normal prediction. Now let's see some results. As shown in this table, just simply combining the depth prediction with normal prediction without consistent loss can already improve the depth prediction accuracy against the baseline method. By adding our consistent loss, we can even improve the accuracy further. Here are some qualitative results. Our method can generate more smooth and accurate depth prediction, especially in the textureless areas, like the walls. Here's the conclusion of this work. For textureless areas, it is easier to predict normal than depths. The multi-view image information can improve the normal prediction accuracy. Also, the depth normal joint learning with consistent loss can generate smoother and more accurate depth prediction. Now is the conclusion of this talk. First, there are 4 requirements of MVS: depth range, accuracy, time efficiency, and computation efficiency. The target surface of MVS is sparse in the 3D space. Therefore, by using hierarchical MVS, we can get higher accuracy and better time and computation efficiency. In hierarchical MVS, we can use uncertainty-aware adaptive sampling to change the depth range dynamically. And by considering the consistency between depth prediction and local geometry feature, we can improve the depth prediction further for textureless areas. In the end, we'd like to show some potential future directions our lab's work on multi-view stereo. First is the unsupervised learning. Since the ground truth of MVS is usually very hard to obtain and requires expensive professional devices, therefore we'd like to study whether we can train the network without supervision and achieve comparable accuracy. Second is we want to use semantic information such as object category to improve the depth prediction. Last is the network acceleration, such as pruning and model quantization, which is crucial for real applications. This is all for this talk. Thanks for listening.